Ladies and gentlemen, my name is Tim Friedhofer. I am joined by Matt Quensler, Matt Borowski, and Mike Mischison. Together, we are the prestigious Fahrenheit 451 Degrees of Freedom. We've been contracted by a large natural gas processing plant headquartered in Houston, Texas, Midline Chemical. They desire that a plant be designed and built in Philadelphia, Pennsylvania by April of 2020, capable of converting natural gas into liquid methanol. Before we proceed, I would like to discuss the final results that we were able to determine. The product specs that we were required to meet were a flow rate of at least 114,000 pounds per hour of methanol product. We were able to achieve a flow rate in excess of 115,000. The purity spec that we had to meet was 99.85%. We were able to make a product stream that was 99.86% pure. At least 90% of the methane in the feed had to be converted to methanol, and more than 91% was converted. So all of these hard specs were achieved. In the end, we required a capital cost of nearly $270 million with a working capital of $4.7 million. Our IRR ended up being 16%. As you can see in this graph, after year 4, we were able to make nearly $32 million in revenue, and after 15 years of plant life, this value has increased to nearly $160 million. Midline Chemical gave us freedom to decide how exactly this plant would be designed, but they required that we follow two major technological methods. The first was that the natural gas feed be converted to syngas, carbon monoxide and hydrogen, using a steam reforming process where the heavy hydrocarbons, the ethane, propane, and above, would be converted in a pre-reformer, and then in the larger, more expensive SMR, the steam methane reformer, the methane would be converted to more syngas. The syngas would then be converted to the methanol using a Fischer-Tropsch process in a shell and tube reactor that will be discussed shortly. Some of the key specs that we had to deal with were the location. We were bound to work with the standards of Philadelphia, so we had to account for any cost issues with this and deal with environmental and safety factors with this location that go with a large city. As mentioned in our summary earlier, the specs that we had to meet were a 90% conversion of methane in the feed, while also achieving a product that was at least 99.85% pure. Our feed was 40 million standard cubic feet per day of natural gas, which is more than 90% methane.
In designing our methanol plant, we have basically 3 stages. We have the upstream in making syngas from the natural gas feed, downstream in making methanol, and of course the purification of the final product. To start off in the upstream part, we have a natural gas feed coming in that needs to be purified before we could actually create our syngas. To do this, there are 2 toxic chemicals, mainly mercury and hydrogen sulfide. Mercury isn't as much of a safety ramification on design, but hydrogen sulfide is corrosive to carbon steel and poisonous to catalysts. To start off with the front end design, we have a mercury absorption tower, as you can see all the way to the left. The mercury absorbent tower has absorbent packing in which we just send our natural gas feed through, and it knocks out pretty much all of the mercury down to the parts per billion. From there, we have treated gas that goes into an MDA absorption tower. The MDA solution is 50% MDA and 50% water. This will get rid of almost, again, all of the hydrogen sulfide. Now, from there, we could go to pre-reforming and steam methane reforming. The natural gas going into the pre-reformer basically knocks out all of the heavy hydrocarbons, which then enters the SMR. The SMR converts our natural gas feed into syngas, which is basically carbon monoxide and hydrogen. The SMR is also a large safety concern as it operates between 2000 and 1600 degrees Fahrenheit. Go ahead. Now, I already talked a little previously about the safety concerns. But the main ones, as I said before, are the hydrogen sulfide and carbon dioxide, which are both corrosive to materials and poisonous to catalysts. And another big factor, especially around the SMR, is high temperature hydrogen attack. At higher partial pressures and very high temperatures, especially around above 1,000 degrees Fahrenheit, high temperature hydrogen could completely destroy any carbon steel. So we're going to have to use high strength, low alloy materials through this. And basically from the front end of the plant, we're going to have to use stainless steel through the mercury absorber and through the amine scrubber. Then we have to go to a high strength, low alloy steel to throughout the SMR and the integrated heat exchangers. After that, we could switch back to carbon steel, as that is most economical for our process. But another safety concern is our flue gas emitter coming off of the SMR. Basically, nitrogen oxide and carbon monoxide also present a problem, so we will need to implement a NOx scrubber. But besides that, the safety ramifications on design are basically, the rest is all carbon steel for economical purposes. Now going into the downstream plant design, this is where we actually convert our syngas from the steam methane reformer into methanol. This has basically three big units, which are the compressor, the FT reactor, and a condenser drum. Now, provided by Knitline Chemicals and our R&D department, we were able to acquire conversion data from carbon monoxide and hydrogen conversion to methanol. This occurs around 7 megapascals or 1000 psi and about 480 degrees Fahrenheit. To do this, we need a series of compressors to get our natural gas feed up to the right pressure, and we utilized a heating shell and tube heat exchanger for the FT reactor. Now what happens is, after compression and we are at operating conditions, the syngas will flow through the top of the reactor down through the bottom, and we'll have a cooling solution of just basic city water going through the shell component in a countercurrent flow. This occurs completely at isothermal conditions to obtain both purity spec and the capacity spec of our final plant or product. Now, a big concern here also on safety is we're dealing with very high pressures here of 1000 psi. So of course gauges on gauge of piping and thickness is also a big concern. And for operators operating around here, are several safety hazards to be implemented to avoid any type of harm. But after the Fischer-Tropsch reactor, we basically knock out our crude methanol in a condenser. Now, we basically knock out all of our liquid methanol that goes on to purification, but throughout the top, we have a whole bunch of unreacted syngas. This gets rerouted through a recycle system to get reheated, recompressed, and back into the FT reactor. This will both maximize conversion while being most economically favorable.
So as was discussed earlier, we now have a crude methanol product that needs to be purified so we can meet our specs. Downstream purification occurs via two distillation towers in series. Crude methanol enters our first distillation column, which is a full reflux column around 25 trays. We knock out any trace syngases that came out with the liquid methanol in the bottoms of the condenser drum previously discussed by Mike. The bottoms product in distillation column 1 is now refined or somewhat purified methanol that also contains a significant amount of water and ethanol still. So this needs to be funneled into distillation column tower 2, which is a total condenser tower and contains about 80 trays. In the bottoms of this tower comes out water and ethanol, and in the tops is our methanol product. This methanol product is about 99.86% pure, and it also meets our product spec flow rate by achieving almost 1,000 more pounds per hour needed at 115,000 pounds per hour. Now, distillation tower 2 heavies need to be properly disposed of. We have a crude mixture here of water, ethanol, and actually some methanol that comes out as well, just due to the nature of distillation towers. In order for a biotreatment facility to accept our water mixed with alcoholic hydrocarbons, we need all alcoholic hydrocarbons to be below a 3% total mass. To do this, we funnel in some extra deionized water to further dilute the crude heavies before we can then send off that to a biotreatment facility where it will be processed. This is our BFD, which puts the overall process in perspective. It contains what was discussed already in the front end process, which was the conversion of natural gas to syngas. It also contains the conversion of syngas to methanol via the Fischer-Tropsch reaction, and also the purification steps I just talked about. So I'll give the audience here a couple seconds to just glance over the entire process. Next, an economic analysis for capital costs was performed. I broke the economic analysis down into an inside battery limits cost, an outside battery limits cost, as well as other capital costs that are involved in initially building a plant. Our inside battery limit cost came out to about $115 million. Now, the big spenders for this were our SMR, around $70 million, our pre-reformer around $10 million, our compressor units were around about another $10 million, our heat exchangers were about $13 million. There's a lot of other equipment we had to purchase, but those are the significant high-value purchases. Our outside battery limit capital investment came out to about $70 million. What exactly did this include? Well, we had to buy the entire site and land where we built this plant. We also had to account for creating product storage facilities, equipment that was involved for utility lines, as well as storage tank and equipment lines involved in environmental and waste disposal. Lastly, we also had other capital costs. These other capital costs came out to about an additional $50 million and accounted for all of the catalysts we needed to purchase for startup costs and startup operating costs, as well as team costs and an additional few other costs. Adding these all together, and with a 20% contingency factor to account for the uncertainty associated with many aspects, especially Icarus, we get a total capital cost investment of around $270 million.
Continuing the economic evaluation, we look at the cash flow considerations. They include revenue, capital costs, raw material costs, utility costs, and business costs. Now, our revenue is basically comprised of only methanol. We do not generate any steam or any other side products on the plant, which could call it efficiency and for the goal case. Our utility costs comprise of steam and electricity, shown here. The steam is both high pressure and low pressure steam. A low pressure steam is of course much cheaper and more utilized in the plant. The business costs are a more large menagerie of costs. They include a corporate income tax rate of 35% on our income. They also include the operator costs. Most operators cost about $80,000 per year, and if you assume about 4 operators per shift and 3 shifts a day, that ends up at pretty much 12 operators total at each $80,000 per year. Finally, process costs include mainly our natural gas cost. Also included in that is our MDEA, catalyst, and things like that. So, to sum up, our revenue approaches $135 million a year, whereas our utility costs, you subtract $32 million a year, our business costs, you subtract another $12 million a year, and our biggest cost, our process costs, we subtract $60 million a year. But moving forward, that gives us a net back of $32 million a year on average, not accounting for inflation or process scale-up, which is pretty significant over 15 years, and considering about 7 years of making somewhere around $32 million a year, we can really put some much needed cash into our cash flow. So looking at the cash flow analysis, there are 3 main things we want to consider. We want to consider cash flow, present value, and net present value, where cash flow is the sum of all cash flows from the previous years forward. Net present value is just the cash flow to, and using the discount rate, calculating what our worth is currently on the market. And the net present value is the cash flow times the present value to give the net present value, because as I said before, cash flow is a sum of all cash flows giving a net present value. Now, what is interesting to note, and probably the most important economic evaluation, is the internal rate of return, known as IRR. This plant gets an IRR of 16%, which is vital to the plant's success. It is greater than 9%, which is the discount rate. The discount rate is the rate at which a bank would essentially give us a loan, or we could get funding through our parent company. So when the internal rate of return is greater than the discount rate, a company will often greenlight a project. Moving forward into the specific part of this cash flow, the most important year in our cash flow is year 8. As you can see here, hopefully it's pretty washed out. Year 8 is when our net present value goes positive, and this makes complete sense because year 8 is exactly when our production scales up to a full 100%, and we've paid off all of our capital costs, and we still get a little bit of depreciation tax credits. So that would really pushes us into the positive for the company by year 8, and by year 15 we reach a net present value of $104 million, which is less than the capital investment, but the company actually makes that above the capital investment. So it is a profitable idea, both from the idea of net present value after 15 years, and the internal rate of return is greater than the discount rate. Both of these are key to approving a capital investment, and according to our research, by 2020, if we start building this plant, it would be a good idea for Knitline Chemical to accept our bid. Moving forward with some recommended issues. We should still kind of tease out exactly what discount rate we might get, but also sometimes an issue with IRR is determining if it's a very short project, you can get a very high initial rate of return, internal rate of return, but you can have a very low net present value. So just kind of realizing with someone who is maybe more of an economist, figuring out exactly if these values are worth investing in. Other areas of improvement that may reduce our process and utility costs are better integration of heating and cooling steams, so we can always have more heat exchangers, increase the capital cost but decrease utility costs. That is kind of a one-time cost versus a continuous cost, so that could save us a lot of money, as well as sending our Fischer-Tropsch initial designs, known as FT designs, to a research group to know exactly the temperature profile within the tube. Considering it is an exothermic reaction, it could be a very dangerous situation if the center line temperature of the tube gets much greater than the other areas of the tube. The Fischer-Tropsch reactor is an area for improvement that is beyond the scope of our current project. Finally, another interesting cost benefit analysis is looking at MDEA regeneration versus what we do now, which is sending MDEA throughout the plant. So MDEA regeneration again will be an increased capital cost, but a decreased utility cost, which could really add up over time. However, currently our internal rate of return says this is a green light project, so MDEA regeneration could just be the cherry on top of the sundae. Overall, we should build this plant. It will make a profit. Thank you for listening.